So we're looking at proving Coulomb's law, the very first formula which we kind of started using in this chapter from Gaussian theorem. So we are trying to go the other way around. Quite simple. So from Gauss's, we are looking at finding the electrical field expression, and from that we are going to the force, right? So that's how it is. The proof starts with considering an isolated positive point charge, isolated being that charge and nothing else. And Gauss uses Gaussian surface, right? That's your Gaussian surface. And that's your positive charge, and this Gaussian surface has a radius of r with center being the Q, right? Now, first thing first, so we have to get an expression for flux. So the flux through a small surface, right, ds. So we always start with a small section of the entire structure. So this has a perpendicular area vector. Area vector by default is perpendicular. And the electrical field also is radially outward. And so these two are on the same line or perpendicular to each other, sorry, parallel to each other. Which two? ds and e. Okay. Next, what do we have? Next, we have the expression for flux. Y or flux on through flux through ds. So that would be a small flux, and this is as simple as writing E ds dot product. Here EDS can be expanded to EDS cos theta, and here theta is nothing but theta is equal to 90 degree. Is that correct? Nope, it is 0 degree. Between E and ds, the angle is 0 degree because they are pointing in the same direction, radially outward, as both are pointing radially outward with Q as the center. And so this small flux can be obtained with EDS. Cos of 0 is 1, so this is EDS. Now, flux via entire surface. So what do? We need to add each and every one of it. How do you add? Well, fancy addition is given by your correct integration, is it not? So your fancy addition is obtained by your integration. So we are going to integrate the field through the entire surface integral. Now, E is constant, right? E is constant throughout the entire surface. E is constant across the entire surface. Reason being, E has same magnitude at all points on the surface S, right? Reason being, the electrical fields are radiating outward, is it not? So you have flux is equal to E ds, as E is radially outward for a point charge. So this is like an axiom. We consider it to be true without any proof. Now, if you add up all the surface, right? If you add up the entire surface, adding entire surface, what do you end up with? We end up with 4 pi r square. Agree? And we know that so we are making use of Gauss's theorem. We have the flux is equal to Q by epsilon naught. Therefore, Q by epsilon naught is equal to E into 4 pi r square. And from this, we can infer that E is equal to Q by 4 pi epsilon naught 1 by r square. Bit of rearrangement and done. Now, force on a point charge Q naught on the surface. On the surface, Gaussian surface that is going to be equal to E into Q naught. That's the whole idea of electrical field. And so on substituting, we end up with Q naught, so on and so forth. And we have proved it. Right? A very simple thing. It's a good point to end this entire thing. And now onwards, it's full of derivations and a bit of numericals. A lot of numericals.